Hi, today we'll talk about an important algorithm, and you can call this algorithm a quantum machine learning algorithm. And it's an algorithm called HHL algorithm, HHL standing for Harrow, Hasidim, and Lloyd, who discovered this algorithm in 2008. Now, this is an algorithm to solve a linear matrix equation. So we have AX is equal to B. And this is a very important problem in linear algebra and has very important applications in all of mathematics. So solving a matrix equation where A is, let's say, M cross N matrix, X is an unknown N cross 1 vector, and B is a known M cross N vector. So these two are vectors. And of course, these matrix equations can be solved by a simple Gaussian elimination. And if, let's say, for sake of simplicity, if we take A to be a n cross n matrix, then we require order of n cube operations by the method of Gaussian elimination. So this is a standard technique in classical linear algebra. Now, this matrix equation, of course, comes across in many branches of mathematics, in differential equations, and also in data science, where we have the matrix consisting of a set of observations, maybe m observations with an n-dimensional data, and B is the output. And so the method of least squares is usually employed, and where this matrix equation has to be solved. Now, the HHL algorithm in the quantum context is an algorithm to solve this equation using methods of quantum computation. So let's write this equation down as an equation that makes sense in the quantum mechanics way. So this is AX equal to B, get B. And let's say we'll take X is X over norm of X, and B is B over norm of. Now, initially, we'll assume that A is Hermitian. So let's assume that A is Hermitian, and let A be also a square matrix. If A is not Hermitian, then we can replace A by and do the analysis on B, which is something of this sort. So the analysis initially can be restricted when A is just Hermitian. Now notice that to solve this equation, suppose A is Hermitian and let's say it's also invertible, then one can just multiply this by A inverse. That is, if A inverse exists, then you get something like this. So X is equal to A inverse B. But even if A is Hermitian, basically there is no linear sort of quantum mechanical operator that corresponds to this. So this is not a unitary operator. And therefore, this technique doesn't work. So let's sort of look at the way we can make it work in quantum computation. So the first assumption that A is Hermitian and square. So since A is Hermitian, A has a spectral decomposition. So let's write the spectral decomposition of A. And therefore, assume that all the eigenvalues are also, so assume lambda j are strictly greater than 0. So A is invertible. So therefore, A inverse will be equal to summation over j lambda j inverse uj. Uj's are the eigenvectors. And then we can write this matrix B, or the vector B, in terms of the eigenvector. So let B be summation over j, some scalars. So this is the expansion of the vector B in terms of the eigenvectors of the matrix A. And therefore, when we write this, then X, which is equal to A inverse B, get B, is in fact summation over j lambda j inverse uj, and then summation over k beta k, and therefore our vector, unknown vector A, is equal to, so uj's are all orthonormal, so uj's orthonormal. Therefore, this can be written as summation over j equal to 1 to n beta j over lambda j uj. Okay, so this is sort of the theory behind the HHL algorithm. And let's see how we'll build the circuit. So the circuit consists of 3 registers. So quantum circuit for HHL. Okay, so the initial, we'll focus on 2 registers before. So the initial part is that we'll have a register that shows that stores our vector B. So let's write this, the initial state, as ket B, and then let me call this as the memory register. And then our other register has ket 0. So this is, so let's assume that we have this initial state. Of course, there is a little bit of theory in how you can load the vector ket B into the register optimally, um, or we want to do it in such a way that the loading step itself is not too costly. So I will omit that for the time being. So the initial step is this. So this, I'll call this step A. And then as I said that A or A inverse is Hermitian, right? So A is Hermitian. And essentially in this solution, we want to get these lambda j's, right? And what we'll do is basically do a phase estimation. So so the second step is a phase estimation procedure on not A, because A is not unitary, but rather U, which is a unitary, equal to e to the I A t. So we'll have to decide on t, but we'll do a phase estimation. Now, what does that do? Now, if we do this phase estimation procedure up for a suitable time, let's say t naught, then the eigenvalues of u are related to the eigenvalues of A, right? Because u is e to the IAT, are e to the 2 pi phi j, where phi j is equal to the eigenvalues of A, lambda j t naught over 2 pi. Right? So if we are able to do the phase estimation procedure on u is equal to e to the iat, we should get back the eigenvalues of A up to some scaling. Right. So assume that we do this, that what will happen is that, well, in step, at the end of step B, we'll get the following in our register. So this will be, so I'm going to write B, this register, as beta j uj. Right? I'm just writing B in terms of the eigenvectors of A. And then I'll have this some approximation to phi j. So I'll call them phi j to R, right? So some approximation. So assuming that we'll do the phase estimation to certain accuracy. So this will be at the end of, now we want, the next step is called an eigenvalue inversion. So this is, so the first step, I will call this as a loading step. Then the phase estimation, and I'll call step C as eigenvalue inversion. Well, we want not phi j, but phi j has to be in the denominator over here, right? So lambda j's have to be in the denominator. So we'll take an eigenvalue inversion step. We'll not go into the details, but it can be shown that one can invert this register in economically. So we can do that in polynomial number of steps. So this is phi j twiddle inverse. Okay, I'll not go into the details of this step. The next step is a control rotation step. So step number D, I'll call this. So this is where, okay, so the control Y rotation. So next step is we'll do a control rotation. And over here, we'll have one more register, which is Ry of theta for a suitable theta. So recall that the rotation step Ry of theta applied to the 0 vector is cos theta over 2 get 0 minus sine theta over 2 get 1. So the next step is a control rotation step, which actually, well, over here we'll add one more register. So the whole algorithm starts out with actually 3 registers. So there is an ancilla register over here, which starts out with 0, right? So this is 0 ancilla. And then what we are going to do is, for a suitable theta, we are going to do a control register in rotation with this being the control register. So control, and this is the target. Right. So what that will lead to is that our state UJM after this step will be summation over J eta J M by J tilde inverse. And since we are doing a control relation with this phi j inverse, I don't have to a priori know what the eigenvalues are. I can sort of create this state. So this will be tensor, just writing it down over here, or lambda j square get 0 ancilla plus c over lambda j get 1 ancilla. So for some normalization constant c, so this will be our basically our cos theta over 2. This will be sine theta over 2, and so on, right? And now at the end of this step, you see that if I just look at this part and this part, then you will see that it is almost what we need over here, right? Over here, that is what we need. So this is we're quite close. And then basically, if we measure a one, that should do it. But unfortunately, we have to add one more step because this register is entangled with um, the first and the um, uh, right. So we have to unentangle this register to make sure that we can just measure um, the the ancilla bit to be a one, right? So the final step, or step E, is called the uncompute step. And so after the uncompute step is what we have is that we reverse the first step, which is basically the first estimation step. And what that leads to is that, so the final state will be beta j uj. So this will be sort of inverted, and then we have square root of 1 minus c. And now if we measure the ancilla state, if we get a 1, then we have our result, right? So let's draw the circuit for this. So I'll explain it through the circuit as well. So we have circuit, quantum circuit. So we have 3 registers. We have register 1, register 2, and register 3. And then we have the first part is the phase estimation part. Of course, we have this is my B, which is in the memory register. Then we have the other register, and this is the ancilla register, which starts off with, so this is memory, this is second register, this is the ancilla register. And then we have this next step is our phase estimation. So e to the I m, I'm drawing the schematic. So T naught, and then F T dagger, right? I'm skipping the second step, the eigenvalue inversion. And then I'm just saying that this is my control rotation step. So this is control, and this is R, Y, theta. And then, so I can sort of take this as the first box. You can say that this is my first step. Phase estimation. Then this part is the control rotation. And then the uncompute step, which is just going to be, okay, so this is not, right, I'll just write it in the opposite order of the first step. So this is FT, this is e to the I minus IAT, and then H tensor N. So this is uncompute. And finally, the measurement over here. So this final step is the measurement step. And we have to post select on one being. Now we can use amplitude amplification to amplify the success probability of getting a 1. Okay, so these are the steps, and so this is uncompute. This is post, so post select get 1. This is the loading step. Okay, so this will be the entire algorithm. And notice that we don't get, we can only sample from this output of X, right? So to actually do something useful with it, we can compute certain expectation values and so on. So one can sample from the output to get some expectation value of observable, right? So that way we can make this output useful. Now, in terms of the optimality or the runtime of the algorithm, I mentioned that the Gaussian elimination takes order of n cube. This is Gaussian elimination. The sort of for a sparse matrix, there is a method called the conjugate gradient, which takes order of n s kappa log of 1 over epsilon, where epsilon is the accuracy with which you find out this get vector x. So this is a conjugate. This is a classical method where S is the sparsity, which is the number of non-zero elements in a row of a matrix. So that is the maximum number for each row. So this is sparsity, and kappa is what is known as the condition number, which is the ratio of the maximum to the minimum eigenvalue. Right. So condition number is sort of a number that is a measure of how much the output changes with a change in the input. For example, if you have AX is equal to B, a matrix is called well conditioned if a small change in B results in a small change in X. So it will have a small condition number. And usually these matrices are easier to invert, and in this case, the the complexity of the algorithm is dependent on this condition number as well. And so for the HHL, it is order of log of n, s square kappa square over epsilon. This was the original complexity for the, it has been further improved now, but I'll just give you that. So this is for the HHL algorithm. So the caveat is that if the matrix has to be sparse and the condition number also has to be reasonably low. Otherwise, we won't get a logarithm, the exponential speed up, but rather if the sparsity is not if order ends, then it'll just be polynomial order, right? So that is the HHL algorithm.